Well, hello everybody. Happy Wednesday to you all. In theory, if it's Wednesday right now and you're watching this, I should be on a bus right now, heading on back for the wonderful state of Illinois, and having a good time on the road, I guess. I don't know. So we're gonna go into chapter one here. Physics Toolkit is what it's titled. Just as a heads up, we are here in Honors Physics. We're gonna go at a pretty steep pace through chapters one and two because the goal is to get to chapter three because that's when it starts to get exciting when we're gonna deal with acceleration and things like that. But anyway, chapter one is a chapter that is not really specific to any particular idea, but it's just a general physics sciencey stuff. Really, so basically, we can't get this party started until we order the pizza, and that's what we're going to basically be doing right here in this chapter. Kind of getting some things set up, and we're going to begin with a definition of what physics actually is. Physics is the study. So get your paper out if you don't have your paper out already. Hopefully you do. The study of the physical world, energy, matter, and how they are related. Physics is the study of the physical world. What that means is I have roughly 100 and what, 60, 70 days with you to teach you about the entire physical world. Kind of a big topic there, but we're going to do the best we can. Anything you could think about in the physical world is what we're going to study this year. Is it, how does light actually work? How am I able to see things? What's going on with sound? How is it that when a vehicle, I press the gas, and if I slam the brake, that I feel like I'm flying forward? Or, I'm on a roller coaster. What makes that ride more fun than that ride? What's this thing about wind energy and all those turbines they're setting up everywhere? All kinds of fun stuff. How do magnets work? How does a circuit work? Electricity. Yes, we're building circuits this year. Anyway, I'm going to get ahead of myself. We need to stay focused. Come on, stay focused, Mr. Gerber. Sorry. Got to stay focused here. So physics, the study of the physical world, energy, matter, and how they're related. Okay? A few things. There is math in physics. As if you probably already learned from the leather lesson earlier. There's going to be some math going on. But I wanted to give you here a little bit of a procedure of how we kind of attack some of the problems that we're going to have in this class. It is, if I take, this Promethean pen I have in my hand right now, if I drop to the ground, if I let go of it, it's going to fall. But there's some questions I have. How fast will it fall? Okay, I highlighted it in blue there. That's something that I can apply a number to. How many meters per second? How long will it take to hit the ground? How much time? Again, that's another number. That's something I can measure. That's something maybe I could predict. But with the power of physics, we can actually know a few of these things and find out the rest of these things. And so in general, a method that I use that I think really helps organize problems together, and I'm going to encourage you guys to do it. We're not going to see this stuff really till chapter 3, but this chapter is a very big, we're going to be using this the rest of the year once we hit that chapter 3. So first thing you're going to do, list out every gnome that you're given with its labels. For instance, maybe you were given, step 1, list your gnomes. Maybe you're given the initial velocity is 12 meters per second. So you'd write VI equals 12 meters per second. Maybe you're given the amount of charge on a piece of nickel is 13 times 10 to the negative 6 coulombs. And you'd write that down. Maybe the luminous intensity of a certain light bulb is 1780 lumens. You write that down. Anything that you're given, write it down with its label. Good thing you keep that in mind. 2, I always list out what I want to know. I want to know the final velocity the pen strikes the ground. I want to know how much time it takes before that battleship intercepts the rest of the Navy. I want to know, how long will it take for sound to travel the length of this football field if it's this temperature outside and the sound is so loud. What do you want to know? After that, generally in physics, there's a lot of equations that are flying around. Okay, I'm going to let you guys keep a formula sheet this year. It's got all your formulas on it. You may use it on quizzes and tests, but only formulas. No, you can't put additional notes on there. You can't have examples or anything like that. It's just got to be formulas only, and I'll be inspecting them on test day to make sure you're good. You can always feel free to show it to me, like, is this okay? And I can say yes or no. But formula sheet, good times. After you have an equation that basically mixes the things you know and gets the thing you want to know by itself, solve it out. Use your algebra skills there. And after that, the crucial fifth step. What fifth step could be there, right? I've solved it. I'm done. What's the fifth step? Doesn't make any sense. Now, some things As you start studying them, you may not have any real, like, I'm not sure if that's really a good coefficient of friction, because I don't know much about coefficients of friction yet. But as we go on, you go, oh, you know what, it's probably going to be less than 1, but greater than 0. Or, we do a speed of sound. You're like, is that pretty fast for a speed of sound? I remember I had a student, I gave a question on a test about if you hear lightning with a certain amount of time, how far away is the lightning? And they used the speed of light instead of the speed of sound. And they said that the lightning was, I can't remember how many, literally trillions of miles away. It was farther away than the sun was. And that's not a good, reasonable answer. Anyway, I chuckled and then I winced a little bit. But make sure your answer is reasonable. If you got a boulder and it comes out to be 30-some kilograms, that makes some sense. If it comes out to be like 5 grams, like 5 paper clips, that's not really good for a boulder. Okay, make your answer reasonable as best you can as you go. Okay, those are the 5 steps for physics problems. Other things we're going to use this year: SI units. It's actually French. It's like Système International, or something in French. That's where SI comes from. I just kind of think of it like the Standard International Units or the System of International Units in English. But if scientists are going to communicate with each other, you got to use SI units. This should be pretty much review. I can't, if I measure, for instance, the length of these tables that you're sitting at. This front row here is from one edge all the way to the other edge of the second table is about exactly 10 feet. Okay, a foot is a standardized unit. It's not the standard international. They use the meter, but it's at least a standard unit. If I could measure it in how many Alex O'Neills it would be. I could lay across. It'd be like, about 1.5. Nah, less than that. It's like 1.3 Alex O'Neill lengths. But if I try to send that off as my scientific result, and someone doesn't know how long an Alex O'Neill is, it's not going to be useful. So we got to use standard units. When you get your textbook, which isn't today, but later, it's on page 5, so maybe you can write that down. So you don't have to have these memorized or anything, but these are actually the 7 base units that everything in science can be written in the form or a combination of these. So let's actually take them one at a time. Let's take them one at a time. I'm just going to talk you through them. You don't really, you can write them down if you want, but they are on page 5 in your textbook when you get your books on Thursday. Length. Length we measure in the meter, abbreviated M. Okay. Mass. Now there's 2 big things I gotta yell or not make sure that you understand. Mass is in kilograms, not grams. The SI unit for mass is actually the kilogram. Okay. A gram is so small, it's not terribly useful. The kilogram is much more useful to us. Okay. Kilogram is about 2.2 pounds. That's the SI unit for mass, is the kilogram, not the gram. The second thing I need you to make sure you understand is the kilogram is a measure of mass, not weight. Really get this, because it's misspoken all the time. You're in chemistry. Yeah, why don't you go weigh how much compound we have there? You go, you put it on the scale, you come back, it's this many kilograms. That is not a weight. You found the mass. In English, we tend to use the word weigh. You weigh something, and you get your weight, so to speak, but be careful. Weight is actually a force that we're going to get to in chapter 4, and that is measured in newtons. It's different. Okay, the English version, pound, a pound measures weight. Yes, it does not measure mass. My mass is not in pounds. My mass is only going to be in kilograms. So make sure, if it ever says find the mass of something, you're actually finding the kilograms. If it says find the weight of something, you're not finding kilograms, you're finding something different that we're going to cover in chapter 4. So I'll emphasize this again in chapter 4, but it's a big one. That mass is in kilograms. Weight is not in kilograms. Weight is going to be in newtons. We'll get to that later. Okay, time is in seconds. It's abbreviated S. You've seen that before. Now let's say I want velocity. Well, that would be meters per second. I don't need a new unit for that because I can make it out of a combination of the previous units. If I want to know acceleration, I could do meters per second. And you get meters per second squared for acceleration. I want to know at what rate does somebody gain mass if they're eating cheeseburgers. Well, that would be in kilograms per second if they're but I don't know why you'd study that. Temperature. SI unit for temperature is Kelvin. We're not really going to play with that too much this year. You played a lot with it in chemistry. We're going to do a little thermal if we get the chance to. Right now, that's one of the things that's on the fence. I got to cover the entire physical world in a certain amount of time, and I hope that we can get thermal in this year. We haven't got it in previous years, but my plan this year currently is to get thermal in pretty close to right after Christmas. When it's cold. Makes sense. Okay. Amount of substance is the mole. Remember that from chemistry. Another one that we're not going to use a whole lot this year, but the mole. And then we've got two more. Electric current is in amperes. We're going to get to that a lot after Christmas as well. When it's actually colder out, less humid, we can do a lot more static electricity stuff when it's drier air. So that's what we're going to do for that. And the last thing is a measure of brightness. Luminous intensity is measured in candelas. Okay, you don't have to memorize these or know these, but just the introduction to the year. That's what Chapter 1's about, is the introduction to the year. We're going to play a lot with these guys, and later we'll play a lot with this guy, and we'll play with this guy, and with that guy, just not as much with those guys. Okay? Good? Good so far? Moving on? Feel free to pause the video at any time if this is going too fast or too slow. Well, you can't really speed it up without my voice going really high-pitched and difficult to understand. Aha! Go. Next slide. Moving to boot the SI system. Woo! The power of 10. Right? You remember your metric prefixes a little bit? Now, again, don't write these down right now. That's going to probably be a waste of your time. But let me tell you about this. It is on page 6. If you're ever doing a problem, you come across micro and you can't quite remember what it was, if you want to write down somewhere in your notes there, page 6 is going to have a chart for you during your homework. Okay, now you might be asking yourself right now, okay, I do know a number of these, Mr. Gerber, but I don't necessarily have them all memorized right now. It's been a summer. Should we memorize these? And I would tell you that you're going to need the vast majority of these throughout the year. Well, we're not really going to play too much with Mega, Giga, or Tera, but a lot of the other ones you're going to see. But they're going to come in context. So what I mean is you're going to do some homework problems maybe in one section that have kilo and milli and centa in it. On the quiz and test, you can assume there's going to be kilo, milli, and centa on the quiz and test. When we get to studying about electricity, you're going to see micro a lot in electricity. Microcoulombs. Because a coulomb is such a massive unit of charge, we end up dealing with micro. So you're going to see micro a lot, so guess what's going to be on the quiz and test? Micro, when we get there. So you don't need micro right now, but you'll need it when we get there. So I don't recommend memorizing all these right now. I mean, if you want to. My chemistry teacher made us say them incredibly, like we had to say all of them in like 20 seconds, so I guess we were like decicenta, milli, micro, nano, pico, femto, atto. I can't forget it because it's been drilled into my brain. You could try that if you want, so everybody with me. Decicenta, milli, micro, nano, pico, femto, atto. I'm kidding. None of you guys were probably with me. Thanks for those of you who tried. Okay, but nano and pico, especially nano, you're going to see a lot of this during light. Wavelengths of light tend to be measured in nanometers. Pico and femto, when you're dealing with the frequencies, are dealing with the frequencies of high velocity or high frequency lasers. You can have some incredibly quick blasts. I mean, they got femtosecond lasers out there that can actually cut steel fast enough that the steel doesn't get hot enough to melt, and so you can actually make very, very straight edge cuts with those lasers because the cut itself, the steel won't melt around it. It'll just simply burn right through that section. It's pretty amazing. So behold the power of 10. The squirrel is beholding the power of 10. You should too. Okay, so anyway. You just got to be able to do it. You don't have to have all these memorized. You're going to have to memorize the ones that we're in, and you're going to have to be able to do it. I'm not going to spend a lot of time on it. You should have learned it before. If you have any questions, you can talk to me, though. We're going to keep moving. Dimensional analysis. Remember doing that back in your chemistry times? When you treat your labels like they're algebraic quantities, okay? And so labels can cancel. When you multiply across, and you can kill things, and it's a good time. Very similar to chemistry, but I'm going to call it dimensional analysis sometimes. I might call it unit multipliers. But the idea is watch your labels, okay? And when you're doing problems, so I'm going a little too fast there. I should slow up a little bit. You don't have to really write the red down. Follow your units through a problem to make sure your answer's units make sense. When you set up a problem, if you plug all the units into the equation, all of the units should work out, and your answer should have the right units. Okay. For example, if I want velocity, you're trying to solve for velocity, you want your answer to come out to be in meters per second. If you get something like kilograms per second or meters per kilogram, then you know something went horribly wrong in your setup. And you can actually detect mistakes that you make in your work by watching your labels. It's a good way to double check some things. Okay? As I look at some of these units, kilogram per second, again, like what would that measure? It would measure a change in mass over time. Whatever that's going to deal with. If something's burning, maybe. Or meters per kilogram, not exactly sure what I would measure with that. Like how tall something is versus how much mass it has. Anyway, so if it's velocity, this is definitely not velocity, I'll tell you that. Meters per second is should come out of velocity. And, guess what happens if you get a problem and it says, the radius of the Earth is, let's see. Maybe the distance from the Earth to the Sun is 1.5 times 10 to the 8th kilometers. Find out the speed of light is this many meters per second, and you have to watch out. Oh, kilometers and meters, and we got to make sure we convert. So real quick little review. I want to convert 43 kilometers per hour to meters per second. I'd just like you to set them up and go for it. Okay, I'm going to give you a minute, see if you remember how to do this, and then I'm going to do it with you as a review. So your minute has started. Go. Keep at it, keep at it. Don't look up here until you have to. Keep at it. Alright, that's your minute. See how far you are, how you're doing. You got to convert, you got to get your kilometers to meters, and there's 1,000 meters in a kilometer. You can either write 1,000. I probably would write 1,000. I feel like writing 10 to the third, because that's what we had a couple slides ago on that chart. But there's 1,000 meters in 1 kilometer. Since this is equivalent to this, I have a fraction where the top and bottom are the same. It's like you're multiplying by a giant fat 1, really. So that's why it doesn't change the 43 kilometers per hour. It's not actually going to change the value. I'm just multiplying by 1. I'm changing the way it looks. So these kilometers will cancel. Now I'm in meters per hour. I need one more unit multiplier to get rid of that hour. That'd be hours to seconds. You can do hours to minutes, then minutes to seconds. Either way, you're going to have to put 2 60s on the bottom, which is 3,600. Multiply your numerators, divided by your denominator. Let's see. Get my calculator here. I'm popping out to about 11.9. I'll just put 12 for right now because I only had 2 significant figures here. I'm going to stay with 2 here. We'll talk about that in a bit, by the way, sig figs. I know you guys are missing them so much, probably, right? Big old summer in there. Like, I miss significant figures. Yeah. Questions? If so, you can maybe pause the video quick. I mean, this video wasn't a whole 40-some minutes. At least I hope not. I'm recording it right now. I'm watching my clock. You can maybe ask your neighbor. So, if you feel like you need to stop this now, there could be a time. Okay, we're going to keep going. Assuming we're good. Feel free to ask me, by the way, guys. I'll be in here tomorrow morning or Thursday morning, depending when you watch this. I'll be in here Thursday morning before school, somewhat all the way until I have to be out in the parking lot, which is at like 8:10 or so. I don't know. So you can come in before school if you can. Okay. I've got a big thing to talk about here, some common confusion. And this is not the precision versus accuracy. The common confusion I'm going to talk to you guys about is not the common confusion you might be thinking I'm going to talk to you about. Okay? Because the time I get students coming to physics, they bring with them some chemistry baggage that I kind of have to help clear up. Precision, when we're talking about a single measure, actually let's just back it up. Let's talk about this slowly. You talk about accuracy and precision. A lot of people think, at least they come to me from chemistry, they think of like a target, and they go, okay, if you have a lot of measures that are like over here, then it's precise because they're together, but it's not accurate. Or you could have another one where you have targets around there, and you go, wow, that's pretty accurate, but it's not really precise. It's not honed in. That is a different word that's a different use of these two words than what I'm going to talk to you about. When I say precision versus accurate on this slide, I'm going to be talking about a single measurement. What about the precision and accuracy of a single measurement? When you're talking about a definition of precision like this, that's where we're talking about a group of measurements. How precise was that group of measurements? We're talking how close are they to each other? And that is one use of the word precision. But when I talk about a single measurement's precision, I'm looking at the exactness of the measurement. Okay? This is for a single measurement. You notice it's not plural there. Okay? A measurement. Precision is the degree of exactness of a measurement. So, if I was to measure the length, again, of maybe these tables, let's say it's about 2.5 meters, just throwing that out there. So let's say I say it's 2.5 meters. Okay? Ish. Well, that's a certain amount of exactness. This is to the nearest tenth, right? To the nearest tenth. But maybe if I measure it using a laser, and actually maybe I could set up a mirror in the back and set up a photodiode on the other side, and send a light down to one side and back again. Use the time frame in there and maybe measure the distance that way. I might be able to get it out to be, say, 2.49623 meters. Are they both accurate? Yes. They're both pretty darn close. Now, if I would have estimated it, said, it looks like 4 meters, then that would have been a terrible estimate. Precision amounts, how many of these decimal places are you talking about? This measurement right here is much more precise. You might say, well, it's also much more accurate. And it's only just slightly more accurate. They're really close to each other. The precision is how exact is your measurement. Did you measure with a meter stick? Did you measure with your eye? That's not really measuring. How did you measure it? When you're dealing with graduated cylinders back in chemistry days, remember those? Some of those graduated cylinders, like your 10 milliliter one, has a little more ticks in there than, let's say, a 500 milliliter one. Okay, you can make a more precise measurement with that smaller one, but it only can hold so much. Anyway, one way to define it is the smaller amount of uncertainty there is, the more precise it is. I just like to think of it as how far out past that decimal have you gone. If I say how precise is it, you could say it's the nearest hundredth. It's the nearest tenth. It's the nearest whole. It's the nearest 2,000. Okay, how far away is the sun from Earth? Maybe you have that measurement to the nearest, 10 million or something like that. The precise doesn't have to be past the decimal point. Accuracy is how well the results agree with an accepted value. For instance, if I'm measuring the acceleration due to gravity at sea level, that's supposed to be somewhere around 9.8 meters per second squared. Maybe I do some drops and things and I get 9.6. Maybe I get 10.1. Pretty accurate then, not fantastic, but pretty accurate. If I get 30.7, then that's so inaccurate, I'm very convinced that I did something wrong with my experiment. So this sort of accuracy is probably the same thing you're thinking of. How accurate, how close is that measurement, again, single value here, to reality, at least the accepted reality. Okay, things change over time. We get things more and more precisely measured. Okay, so how close it is to the real value determines accuracy. You get the difference? Okay, I'll be here. We're not going to get all of Chapter 1 done today, by the way. We're going to get through a good chunk of it. Because on Thursday, I got to get you your textbooks to you, get you your syllabus, talk about class rules, some good times there. And then we will finish the chapter as well. About 2 slides to go. Okay? And yes, they are about your favorite science topic. Significant digits. Woo! You know, I bet if you cheer loud enough, I can hear you on the bus. Probably bad idea. Bad idea. Don't do it. Okay. Quick review of which digits are significant and which ones are not. All non-zeros are significant. If you want to write down these rules, may not be a bad idea. If it's been a little while, if you're a little rusty on them, that's fine. Something you can be studying. All non-zeros are significant. Leading zeros are never significant. They never do anything for us. If you're curious why we deal with these, I plan to tell that to you when I'm back on Thursday. Okay? I went all the way until I was in college before I figured out what the heck these things were even about. I just followed the rules. I want you guys to really understand it too, so I plan to talk it to you when I'm here in person. What I refer to as in-betweeny zeros. In-betweeny zeros are zeros that are between significant digits. And those are significant. Zeros that are in between significant are significant. So maybe I should write a number up here. 0.003407. Okay, here's a number. Leading zeros are never significant because I can write this number. I can write this number as 3.407 times 10 to the negative third. Notice I could write it without those zeros there. The zeros aren't really holding a purpose that's necessary. You could say that they weren't measured. Okay, the things I measured are actually these numbers out here. That's what I read off my chart, so to speak. I didn't read those, I didn't measure those zeros. Okay? Leading zero is not significant. In-between zeros are measured. When I use my, if I'm using a meter stick or using something, I guess this precise, maybe it's a balance or something. It's a balance that's really, really sensitive. It can measure out 6 places. That zero is measured. Okay? Not only is it, because, well, first, you could think of it this way. Like, how am I going to, there's no way I can really shorten this up to have that 7 in the right place. The zero is not just a placeholder, though. It's actually, I have zero of what place is that? 100 thousandths. I have zero measured at that spot because I have 7 of the millions there. Okay? And so I know I have none here. Anyway, because this guy's right here on the end, I know he's significant. Okay? Because I know that place was measured. I measured past it. That means I had to have measured that. Ending zeros are significant in the presence of a decimal point. Let me talk about that, okay? Write it here first. Ending zeros are significant in the presence of a decimal point. Yeah. Let's say I said there were 75,000 people at a certain college basketball game or something like that. Do you think there was exactly 75,000 people? Or do you think that's kind of a rough rounding, right? There's a little bit of a round off there. Maybe I did have it to the nearest 1,000, right? This we measured to the nearest 1,000. So is it very precise? Well, what am I comparing it to? This is measured to the nearest 10,000. But maybe a different measure was 75. It was actually 75,300 was the next measure given to you. People at the game. Okay? This is a more precise measure. It goes to the nearest hundreds. But again, these zeros, I don't know for certain that there were exactly 75,300 people. Maybe there were 12 more. I didn't have that in this measure. It was only measured to the nearest hundreds. I have 3 significant digits here. These zeros aren't significant. Same here, these zeros are not significant. It was only measured to the 10,000ths. This number written in scientific notation would be 7.5 times 10 to the 4th. This one would be 7.53 times 10 to the 4th. See what I'm talking about? What if I did measure it down to the nearest tens, a more precise measure? 75,330. More precise now, 4 significant digits. What if I measured it all the way down? 75,300 and it happened to be exactly 30. How do I tell the difference between these two? I put a dot right here. Now I know that this 0 was measured. In the presence of a decimal point, you now have ending zeros being significant because they were measured. Does that make sense? So zeros past the fact are significant in the presence of a decimal point. Without that decimal point here, then I can't tell you, those weren't measured. Those are just rounded off. Okay? So decimal point, in the presence of a decimal point, we get these zeros to be okay. If I put a 0 right here, that 0 is significant because of the decimal point. It's a trailing 0, a 0 on the end, but in the presence of a decimal point tells me that I actually measured this place. It happened to measure a 0, but I measured it. It's not an unknown where I may not know these digits. If I was measuring the length of a table, how many digits does the length of a table have? Infinite. That's fun to think about, right? I'll never actually know the length of a table. I can measure it all I want and use the most accurate tools I've got, but will I ever know it exactly? And the answer is no. In fact, the molecules are vibrating to the point where it's actually a changing quantity. But I can measure out so many places with technology, but eventually there's unknowns. This could be 126,932. It could be like pi for all I know. It could be irrational. I just about to pull my headset off. Whoops. I was excited. I don't know. So there's going to be a spot where the number stops. The precision stops. The instrument you're using to measure with stops. So if you measured that 0, I would put it. If I didn't measure this, I wouldn't write the 0 there at all. I would just stop with the 7. But if there's no point in putting zeros because I don't know. But if I do know it's a 0, I need to write it. Okay? That means those are measured. That gives me more significant figures. When you do your math with significant figures, sig digs, if you will, significant digits, the result can only be as precise as the least precise measurement. Okay? The result can only be as precise as the least precise measurement. I want to talk to you guys about this again tomorrow, but I'll say a little bit here now. If you have, so let me scroll that down. Finish, let you write that down. When doing math, the result can only be as precise as the least precise measurement. Okay? If I measured like an ant traveling a certain path, I don't know, like this. Let's say I measured this one. I measured it all with a ruler, and I had that this here was 29.2 centimeters. This one here was 10.2 centimeters. This right here, maybe I measured this with I had a different tool I could measure with. Or maybe I did in the last one. Let's measure them with the ruler. Never mind. This one with the ruler, maybe I came out with 12.2. But then here, I'm not sure why they're all 0.2. I'm just feeling like it. Here, I measured this one with a more precise instrument. Perhaps I measured it to be, let's see, 27.296 centimeters. I was able to measure that one out to the nearest thousandth of a centimeter. Pretty precise. Now, if I ask, how far did the ant go? When I add these together, I cannot, I'm just going to add them up just as they are. I'm making this up on the fly right now in case you couldn't tell. Come right here, 12.2 plus 27.296. I'm getting 78.896 centimeters. I could not, as a responsible scientist, report that as the measure. Why? See, this is why I want to be here. I want to hear your discussion. Because I don't know what little trailer decimals there could have been on the ends of these. There could have been some extra digits here and extra digits here. There probably is. I didn't measure it that precisely. So for me to tell you the ant went exactly this far would be bologna sauce, as my grandpa would say. Okay, bologna sauce. I don't know these digits. I only measured to the nearest tenth on all of them. I didn't measure the hundredths on all of them. I didn't measure the thousandths on all of them. Only the tenth. So I can only report to the tenth, which in this case, oopsies, would be 78.9 centimeters. You're like, well, aren't you losing information? It used to tick me off as a kid. When I was younger, and I shouldn't say a kid, as a high schooler. I was like, why? But I have those digits. Don't they mean something? I measured them. It's frustrating, I know, but if you report this, you're a liar. You're a fat liar, because you would to be able to report that far, you would have to measure all of them that far to really make sure all the little runoff adds up to these digits specifically. You don't know these. So your total sum can only be as precise as the least precise measurement. When you do math, the result can only be as precise as the least precise measurement. Thumbs up? Okay, I want to do 2 of these real quick with you, and then we're going to call it a day, all right? We've got an addition problem and a division problem. If you remember addition and subtraction, you watch where the decimal point is. Multiplication, division, you count how many significant digits there are. This is all in Chapter 1 when you get your books tomorrow if you ever need additional playtime with it. There will be a quiz, by the way, sometime next week. I don't know when. I'm in Tennessee. Why don't you go ahead and try both of them? I'll read them to you. If you're writing them down, that'll make it easier for you to write down. 6.201 centimeters plus 7.4 centimeters plus 0.68 centimeters plus 12.0 centimeters. Number 2, 13.78 grams divided by 11.3 milliliters. Okay? Go. Give you maybe a minute. If you understand something and your neighbor doesn't, it's your responsibility to teach them, by the way. We're a team in here. Labels. Okay, it's been a minute. I wrote up there what you would get on your calculator if you punched all the numbers in. You may not have your calculator today, so maybe you just want to write that down. But then what are we round to? Look at number 1. What was my least precise measurement? This one went all the way out to the 100,000. In addition and subtraction, remember, you're looking at the decimal point. Alright, so this one goes out. I got 3 decimal places. I only have 1 here. I have 2. I have 1. 1 is my least precise is to the nearest tenth. I only can respond to the nearest tenths. Gives me 26.3 centimeters would be my response. Copy that? Nearest tenth was the least precise. Now in multiplication division, you're checking how find the number. For multiplication division, you count the number. Count the number of sig digs, and you report your answer the smallest amount that were there. This one has 4 significant digits. This guy only has 3. My answer, therefore, can only have 3. Doesn't matter where the decimal point is. Now, you might be thinking that doesn't make any sense. You were just talking about precision and it doesn't have to be past the decimal point. With multiplication division, it's like you're looking at areas and volumes now. And I can, hopefully when I'm here tomorrow, if you have questions about that, I can show you a little bit more with a picture of why the rule does seem different here. It's actually the same rule, but geometrically, this is what it translates into when you do multiplication division. So I have 4 here, 3 here. My answer can only have 3. So I need to do 1.22 grams per milliliter. That is my G, grams per milliliter. Capiche? Caposh? Kabosh. All right, that's it. Keep working on that worksheet, and I'll see you Thursday.